Okay, I gotta make sure you guys are good at problems 12 and 13. Here they are. How does the 200-watt bulb look when it is put in the series circuit, and why? Okay, I want to remind you, when I put that 200-watt bulb in the parallel circuit, it's really, really bright, okay? But when I put the 200-watt bulb in the series circuit, do you recall, how does it end up looking?
Dim.
Dim. I mean, to the point where it doesn't even shine, correct? It's not even shining. And so I need to make sure you guys can answer that question. So here we go. Here comes my series circuit, 120 volt. I want to remind you we have a 60-watt bulb here, but I put that in quotes because it's called 60 watts with the expectation that you would put 120 volts across it, but we're not doing that here. So instead we're going to refer to it as a resistor, 240 ohms. This is another 60-watt bulb, so this is also 240 ohms, but this is my 200-watt bulb. Do you guys remember, is the resistance of the 200-watt bulb bigger than 240 or less than 240?
Less than this.
Good. Why? What equation, what power equation assures us that a 200-watt bulb is going to have a lower resistance than a 60-watt bulb?
V squared over R.
Yeah, P equals V squared over R, right? Power equals V squared over R. Big power, same voltage, 120, smaller resistance. Okay, great. So here's my next question now. Why is this guy who's approximately 80 ohms, approximately 1/3 of those, I'm not going to do the math, 60 is approximately 1/3 of 200, I guess. Tell me, why is he dim? What's going on here? Yes?
Well, if they're all receiving the same current.
Just a second, let me stop you there. And in fact, I'll use a different, I'm sorry to interrupt you, but that's so incredibly important. If you want to get credit for this problem on your exam, you have to include that they're in series and they all get the same current. Go ahead.
Okay, and then using the formula I squared times R, because the current remains the same and the resistances are different, then that means the overall power is going to go down.
Awesome. You guys okay with that? They all got the same current, but by I squared R for power, he's going to have 1/3 the power as these guys. He'll be 1/3 as bright. You don't even get to see him. Okay? That's the first question you have to be able to answer, why he's dim. The next question you need to be able to answer is why it is when he's in the circuit, the 60-watt bulbs, well, you tell me. Are the 60-watt bulbs brighter with him in the circuit or dimmer with him in the circuit? Hey, let's find out.
Isn't it a 60-watt bulb? I'm paying attention.
Can you tell the difference? This is the circuit with 3 60-watt bulbs. Okay. This is the circuit with 2 60-watt bulbs.
Right.
And can you tell that that's brighter now? I hope you remembered. Okay. So my question to you is this: why are these 2 bulbs brighter? If I can draw the other circuit, okay, here. This is 240 ohms, 240 ohms, 240 ohms. Why are these guys brighter in this circuit than in this circuit? Yes, Gavin?
They're brighter in that circuit because they have less total resistance.
They're brighter in this circuit because this circuit has less total resistance. Someone besides Gavin, tell me, because this guy has less total resistance, which quantity is going to be bigger for this guy than that guy? Yeah, Cole?
Voltage?
Okay, the voltage is 120, so that's not changing. Okay, so when you say voltage, be specific.
For each bulb, the voltage would be increased because of less resistance. So the 200-watt bulb.
Okay. Cole is thinking of it a different way. Cole is going here, the voltage is just split 3 ways. 40 volts, 40 volts, 40 volts, okay? But how much voltage is this guy going to get? Not much. So since he's getting not much, what's going to happen to the voltage that these guys are going to get? More than 40. So that's great. More than 40. Alrighty. That'll work. But I want you to think in terms of current. Okay? If this circuit has less resistance, what's going to be true about the current? Oh, what's that? Yeah, thank you. There's going to be more current, right? This eye is going to be bigger than this eye. This eye is a teeny weeny eye. This eye is a big eye because this whole circuit has less current. So each of these circuit elements is going to get more current, meaning more power. So if you say it that way, I'll give you full credit. If you say it the way Cole is thinking about it, which is going, hey, instead of 40, 40, 40, this guy gets not much voltage, so these guys get more than 40, and that's why they're brighter, that's okay as well. However you want to think of it is fine. You see it? Yes?
Can you repeat what you were saying about like the first one with the...
Here, because this current here is going to be bigger in this circuit than in this circuit because the total resistance of this circuit is less than in this circuit. You got 120 volts, 120 volts. Here, you've only got 560 ohms. Here, you got 720 ohms. So because you have less resistance, you got more current. More current means these two guys are going to be brighter because they stay the same resistance. They're 240. Hey, I'm going to ask you one more question. I've got here, you see this bulb? This is a 25 watt bulb. Here, if I just took it out of the package. 25 watt bulb. I'm going to put this in the circuit. Tell me, what's going to happen to those two light bulbs when I replace the 200 watt bulb with the 25 watt bulb? Are they going to get brighter or dimmer?
Dimmer.
Let's have a vote. How many people say these two guys are going to get brighter? How many people say these two guys are going to get dimmer? Beautiful. And someone explain to the class, why are they going to get dimmer? Yes.
Same current.
Okay, they're all going to get the same current, okay.
Because it has more resistance.
Thank you. This guy's going to have way, way more resistance. I mean, it's almost like we're going to replace this 80 ohm with like a 500 ohm. Yeah, so because it has way, way more resistance, things are going to be looking a lot dimmer. In fact, let me show you. Let me see if you can tell the difference. 200 watt, 25 watts. Did they get dimmer? Yeah, like a lot dimmer. Okay, all right, well, cool. Hey, it is now time to do the fluorescent bulb demo. See how we're doing on time. All right, here, let's see, that's off, okay. Here comes the fluorescent bulb. First of all, fluorescent bulbs, it's kind of weird because there used to be two types of bulbs, incandescent bulbs, which was just a wire that got really, really hot and got so hot it glowed white and that lit your room, and fluorescent bulbs, which I'm not going to talk about how they work. But they're both becoming obsolete now. What are they being replaced with? Yeah, LEDs, like this classroom. These are all LEDs. Because what made fluorescent bulbs better than incandescent bulbs is fluorescent bulbs use less energy. Well, LED lights use even less energy still. So that's it. I mean, your children will not know what incandescent or fluorescent bulbs are. Your children will grow up in a world where the only type of lighting will be LED lighting. It's kind of weird, you know? And of course, it's weird for me because incandescent bulbs tend to be in the yellow part of the spectrum, whereas LED bulbs tend to be just white or blue. So I don't know, everything looks different to me now. I don't like LED lighting, you know. But okay, great. Hey, get ready. Look at number 14. How do you know that the fluorescent bulb uses the most energy when it's first turned on? The way you're going to be able to tell is by looking at those two bulbs. When I first turn it on, when he's struggling to light, so for the first like 3 or 4 seconds, you're going to be able to see evidence that he's, you know, what do you call it, using a lot of energy. And then when he lights, you will see evidence that it is not using much energy. Here we go. You ready? 1, 2, 3.
Oh.
Okay. What happened to the? Someone describe what happened to the two incandescent lights when it went from, you know, it's struggling to light and then suddenly it lights? What happened to the two incandescent lights? Just tell me, what, did they go bright and then dim, or did they go dim and then bright? The two incandescent lights. Yeah, they went bright and then dim. Right here, let's look at it again. Okay, right now they're bright and then they go dim. You see that? In fact, it's even more clear when I cover up the fluorescent light with this thing, right? Here, they go bright, then they go dim. Okay? So tell me, what's your evidence that the fluorescent bulb is using the most energy when I first turn it on?
I don't know.
Gavin knows.
I definitely don't.
No, yeah. Well, maybe he does. Well, okay. Hey, I don't want to, you know, beat this dead horse, but because these guys are bright, tell me, is there a lot of current in that circuit or very little? A lot of current, right? So that means the fluorescent bulb is using a lot of energy because there's a lot of current in the circuit. And then the fluorescent bulb gets lit and then the lights go dim, which means how much current is in the circuit now? Very little. So it's not using, oh yay, more paper. Is that from Mr. Edwards?
Yeah, pretty much.
Oh, right over here, young man. Oh no, maybe, could you put that paper on top of that bookshelf? No, I'm kidding.
You can do that.
Hey, you realize? So hey, I'm just going to tell you the answer, okay? I know it's using the most energy when first turned on because a lot of current is going through the circuit. That's why the two incandescent bulbs are lit brightly. I know that it's not using much energy after it lights because not much current is going through the circuit. So here comes my last question, okay? The fluorescent bulb. It goes from warming up to getting lit. And when I say getting lit, I don't mean the way you guys mean it. I mean it's getting lit. Okay? So it's warming up and then it gets lit. The resistance, does the resistance go from high resistance to low resistance when it goes from warming up to getting lit? Or the resistance going from low resistance to high resistance? And I want to remind you, when it's warming up, wait, what am I doing? No, I should have it this way. What am I thinking? When it's warming up, does the resistance go from high to low? No, wait, God, I'm all confused. No, I had it right the first time. Well, that got captured on video. So you go, okay, when it's warming up, is the resistance high? Then when it gets lit, does the resistance go low? Or while it's warming up, is the resistance low? And then when it gets lit, the resistance is high? You guys ready to vote? How many people say while it's warming up, its resistance is high? That's why the other two incandescent bulbs are brightly lit. And then once it lights up, the resistance goes low. That's why the two incandescent bulbs suddenly go dim. Does that describe what happens? How many people say that describes it? Okay. How many people say, no, while the incandescent bulb is warming up, its resistance must be low because the other two incandescent bulbs are bright. And then once it gets lit, then its resistance must be high. That's why the two incandescent bulbs go dim. How many people say it's the second one?
Yeah.
Okay, thank you very much. Yeah, it is the second one. Logan, how did you know? How did you know? What was your thinking? How did you know it was the second one?
Well, if you have a high current, voltage isn't changing, so the resistance must go down. And then if you have a low current, it's the opposite.
Yeah, beautiful. Sure. Yeah. High current, low resistance, you know? And I want to remind you again, our 200-watt bulb, that's a low resistance bulb, right? My 25 watt bulb, that's a high resistance bulb. Whenever you've got a circuit element with a high resistance, it's gonna be using very little power. When it's got low resistance, it's gonna use a lot of power when it's in a series circuit, you know? Or no, when it's in a parallel circuit. When it's a series circuit, it's opposite. Well, anyway, I'm not gonna confuse you anymore. Okay, let's go on. Let's do internal resistance of a battery, then we'll be done. Let me get this over here.
Don't hit me.
Keeps hitting your boyfriend.
Okay,
I'm not hitting you.
this over here. Yes? Sure.
I do one in San Diego.
Yes? Sure, why not? Does everybody aware the backside of this Xerox is tonight's homework? Backside, the 5 more electronics problems is part of tonight's homework. Here we go. I'll make sure that this, okay.
Girls, always trying to get your business.
Telemarketer. Just a second. Oh, it's my brother. Oh, please don't be bad news. Hey, Lance. I'm teaching. I have about 13 more minutes before I'm done teaching. She just got disconnected. Oh, I lost service. I'm hoping there's nothing. I mean, anymore, whenever my brother calls, it's like, okay, what happened this time?
It's like me.
Here, just 1 second. I lost service. What is it with this stupid AT&T? Oh, now I got 5 bars.
Oh.
I think it's Donald Trump. He's cutting my service because he knows I hate him.
Only Trump supports that service.
What I'm going to teach you is actually pretty easy, so it's no big deal. I don't.
Should I just pause it then?
Yeah, Lance, yeah, I'm still teaching, but it's not an emergency. You're not in the hospital or anything, are you?
Oh,
Okay, great. See you later, Lance. So it's nothing, no emergency or anything. Okay. Talk to me.
why am I so warm?
That's what you saw.
Okay, well, they make provision for that. We'll talk about it. See you later. Bye-bye. So my brother, he like, sometimes he's not good about paying his bills. So he hadn't paid his auto insurance for like 3 months. And so his insurance lapsed. So when he got in that accident yesterday, he was uninsured. So I don't know what's gonna happen to him now. Wow, this is just really, my brother, he's just got really, really bad luck here.
Isn't he supposed to be the more responsible one?
No, I don't know.
Because he's older?
I don't know. Wow, his insurance lapsed. I mean, you have to really miss a lot of months. See, me, I take my auto insurance directly out of my bank because that's the one payment I never want to be late on. Well, we'll see how that goes. We're out of here in 6 minutes, right?
I think that's
Okay. Internal resistance of a battery. Okay. The internal resistance of a battery. I'm going to call it R sub I. Here's the demo. I have a 6-volt battery here, and do you notice on this voltmeter, if you look at the needle is at 6 volts. If I disconnect one of the leads of the voltmeter, it falls down to 0. Then I put it back and it rises to 6. Are you able to see the motion of that needle? Here it's at 0. Now it's at 6. Okay. The next thing I'm going to do is connect the positive and negative terminals of the battery together. I'm going to connect them with this wire, this bare wire. I estimate that the resistance of this bare wire is approximately 0.01 ohms. So V equals IR. I've got a 6-volt battery, and I'm going to connect a wire that's 0.01 ohms across the terminals, which means my current should be 600 amps. Is that little battery going to deliver 600 amps to me? Not even close. I mean, your wall socket, the best you can get out of your wall socket is 15 amps or 30 amps before the breaker switch activates. 15 or 30. I'm not going to get 600 out of that. Your automobile battery, your 12-volt battery in your car, right? The best it can give you with cold cranking amps is going to be like 200 amps. Your car battery can't give you 600 amps. So there's no chance this guy's going to give me 600 amps. So something's got to give, and I'm going to show you what gives. Okay? Please observe when I short out the terminals, watch the voltage, watch that needle. Boop. What does the needle go to?
Almost 0.
Yeah, now I disconnected. Now what's the needle? About 6. And then I short out the terminals, and it goes to 0. Then I unshort it, and it goes back to 6. What gives is my 6-volt battery ceases being a 6-volt battery. My 6-volt battery turns into a 0-volt battery. And there's a reason for that. And the reason is because of the internal resistance of the battery. So let me show you that now. Internal resistance of the battery. Boy, I'm sorry, this is going to be fast. Whenever you have a battery, okay, your battery actually consists of your voltage source, which in this case is 6 volts, and the internal resistance of the battery. And they are together. The internal resistance of the battery is inherent inside the battery. It's innate to the battery. You know, battery has anode, cathode, and electrolyte. Well, the anode, cathode, and electrolyte together have resistance, okay? Resistance to the flow of charge. It's not like I can just go to that battery and cut it open and remove the internal resistor. It doesn't work that way. The internal resistance is just inherent to the battery. So the next question is, how do I find that internal resistance? And I'm going to show you now. This is the positive terminal of the battery. Remember, I don't have access to that point. That point's inside the battery. I can't stick a lead inside that battery. So here is the positive terminal of the battery, and here is the negative terminal of the battery, right there. And I'm going to attach a small resistor across my battery. Not 0.01 ohms, but maybe 10 ohms. And then I'm going to get my voltmeter, and I'm going to measure the voltage drop across this 10 ohm resistor. This is my voltmeter. Now you'll notice my voltmeter is actually attached to the positive and negative terminals of the battery, but it's also getting the voltage drop across that 10 ohm resistor. So it's getting both. It's getting the terminal voltage, the new terminal voltage, and the voltage drop across the 10 ohm resistor. Let's suppose my voltmeter tells me 5 volts. My voltmeter tells me, hey, I'm attached across the positive and negative terminals of a 6-volt battery, but I'm only reading 5 volts. By knowing this information, I can get what the internal resistance is. And if the bell rings, please don't leave, because we're almost done. To get the internal resistance, step 1, get the current through R sub I. But I hope you notice the current through R sub I is the same current that's running through this entire circuit. Same current. So if I get the current going through the 10 ohm resistor, which has a 5 volt drop across it, then I get the current through the whole circuit. Well, in this case, I hope you see 5-volt drop, 10 ohms. The current ends up equaling, I'm almost done. 5-volt drop, 10 ohms. I'm so sorry to keep you. 0.5 amps. So now I know the current is 0.5 amps. The second thing I'm going to get is the voltage drop across, we're almost done. Oh, I'm so sorry. Across R sub I. Here's R sub I. This voltage here is 6 volts. The voltage here is 5 volts. What's the voltage drop across R sub I? Yeah, 1 volt. It's 6 volts minus 5 volts, which is 1 volt. And so now we get step 3. R sub I is going to be the voltage across R sub I divided by the current going through R sub I, Ohm's law. The voltage across R sub I is 1 volt. The current going through it is 0.5 amps. And so R sub I ends up being 2 ohms. And so let me ask you one last question. Someone who's really bright, tell me, knowing that R sub I is 2 ohms, what's the highest current that this battery is going to be able to deliver for me? The highest current such that it gets to 0 volts and that's all she wrote, it can't give you anymore. What's the maximum current that I'm ever going to get from this battery? Say again? 3. Yeah, 3 amps. Because once I draw 3 amps gives me a 6-volt drop across R sub I. It's no longer a battery. Now I don't get anything out of it anymore. It's 3 amps is the max. Okay. All right. Thanks a lot, guys. Maximum current, 3 amps. Good luck, you guys. Bye-bye.